I barely kept up in the first talk, so if you get a head start.
Well, yeah.
So welcome everybody to the final talk of today. And we have, again, Kuikui, who is going to talk about geometry of polynomials.
Thanks for coming back for the last talk of the day. So I guess what I planned for this talk to be about is primarily around the sort of polynomials perspective of things. Okay, and we'll see sort of, I guess, methods for establishing spectral independence using very more like algebraic or analytic tools in the study of polynomials. So I'm going to do it like a little sleight of hand here. So I'm going to switch settings where the distribution mu is supported on fixed size subsets of a finite set. This is really just for convenience. I can always homogenize using, say, this coordinate assignment pair trick and so on. Okay, so but I think for convenience, I'm just going to assume it's supported on a fixed size subset. So you can maybe think, for example, uniform distribution over spanning groups. We'll see some more examples. Okay. Yeah. So I'll be a little bit informal about this. Okay. Okay. So what is the rough theme behind this type of approach? Well, the theme is the following. So I have a distribution over collections of stuff. So I can encode this distribution using a big multivariate polynomial, or I have a variable zi for every single element in the support or in the ground set of my distribution, and then I have a monomial and then a coefficient for every element in this, for every set in the support of the distribution. Sorry, yeah, good catch. So here z to the s is just I take the product of all elements in S and take zi. Okay, so this is a k homogeneous multi-affine polynomial. Multi-affine meaning there's no like x squared in there at all. And it's k homogeneous, all monomials have the same degree. Okay. Yeah, and let me just recall, so just remind you what the conditional influence, what the spectral independence is. It's the analog for the fixed size situation. So if I have two elements ij, given by a difference of marginals, sample a set from my distribution mu, the probability that j is in the set, distribution on I is in the set, minus the probability that j is in the set. And notice here, things have changed slightly where I no longer condition I being not in the set, but okay, it's essentially the same quantity. And then spectral independence just says that largest eigenvalue of this guy. And then all of the mixing results go through. Okay. Okay. So again, the main thing is I want to use analytic or algebraic properties of this multivariate polynomial to do something nice about the correlation structure of my distribution. Okay. So this is actually this approach actually has a pretty long and rich history. Let me just give you like one example of a result from many years ago of this flavor. Okay. So it's an example. Here. We'll see how this type of thing can be useful for spectral independence. So there's a theorem of Porchea. And figure 9 says the following. So if g mu of z is non-zero whenever the imaginary part of zi is positive, while I. Okay, so you think of this as being, for each variable I draw the complex plane, it's going to be zero free in the upper half plane. Okay. Then for all I and j, I have the following correlation inequality. Probability that j, s, conditional I is an s, at most. Okay, so in particular, the distribution is negatively correlated. So this is like one example of very classical result that says, if I have some really big zero-free region, I can deduce something about the correlations of the distribution. Okay, and this has many applications. This is a particularly nice and robust notion of negative correlation. Has, for instance, so these types of polynomials are typically called real stable polynomials, and they were instrumental in like for instance, the breakthroughs of Marcus Spielmann and Srivastava on Katz-Singer and constructing Ramanujan graphs and so on. Okay. This is an example of type of theorem in the space, and now I want to use. So now I want to use this for related type or prove related theorems for establishing spectral types. Okay, so that's the whole theme of this talk. Okay, so they're essentially. Okay, so there are at least, okay, so there are two properties that have so far been useful in the literature. So properties, although of course there may be many more undiscovered. So two properties that have been useful. So I can think of g of mu as a function on, say, Rn. I can ask that this thing is log-concave. And why you would ask for it to be log-concave and not something else, okay, you'll see in a moment. So this is one example of an analytic property of distribution for the polynomial that I'll be able to use to deduce something about my distribution. And the second is just that, similar to this theorem, g mu has a large zero-free region. Maybe not the entire half plane, but sufficiently large. And I'll be more precise about what that means. Okay. So the final talk is I'm just gonna like show the connection with log-concavity, and then in a separate sort of part of the talk about zero-freeness. Okay. So I guess really the main connection here, which is perhaps the main takeaway of this talk, is and why you can even deduce correlation inequalities from properties of the polynomial is the following connection. So it's following lemma. Here's a lemma. This is just, okay, so this says that I can recover probabilistic quantities by differentiating my polynomial. Okay. So for all I look at the probability that I is in a random set S. This is equal to, if I differentiate the log of the polynomial, and I evaluate it all once. And the second thing is if I differentiate again, I get correlations. So for all I and j, say all I not equal to j, the probability that I and j are in S minus the probability I is in S, j is in S. This is equal to, if I differentiate twice. Okay, so I've written probabilistic quantities in terms of analytic quantities, and so that's really the crux of the connection. Okay, so does anyone want to tell me a proof? Yeah, you just differentiate, right? I mean, when you differentiate, use multilinearity, that it will pick out all the terms that contain the variable. That's it. Okay, so if I look at this thing, this is really a summation over all sets that only the ones that contain I will survive. Maybe I remove I from it, but if I evaluate all once, I just get a sum. Okay, and then if I just do the calculation over and over again, okay, well.
Log is to get to normalization.
Again? Yeah, I guess so. Technically, you don't. So Okay, at least for this one, it doesn't make a difference because G mu is normalized. Okay, sure. But for this one, you needed to get this extra term. Okay, so if you only differentiate G mu itself, you only get this point. This is really a correlation. But you can look at either one. It's just more like traditional to look at log. Okay. Okay, good. Okay, so now I can state what is connection between, say, okay, so now what is log concavity? So I'm going to talk about log concavity now. So it just says the following. So it just means that I look at the Hessian. Okay, sorry. Just before I say this. So I look at the Hessian of the log of the polynomial. This is -7. Let's just say simplicity at all ones, but okay, you can ask for it for any points. So this is like just the classical definition of log concavity when I have a function. Okay. All right, so what's the connection? So we're going to use kind of this lemma to translate what this thing is to what's the spectral independence. Okay. So in particular, this is a definition. So the following are equivalent log concavity. Same thing as zero spectral independence. Just like the best you can hope for. So think about, for instance, the complete, like I have everything, like it's uniform over all case sets. Quality or an equivalence, you can already kind of see it through this thing, through this lemma. So maybe just to, all right, so I guess does everyone believe this, or should I? But so okay, so I won't spell this out, but what I do want to do is sort of give you sort of more like generic dictionary between sort of three communities of people who use different language. So give you another dictionary. Really, I have there are three communities of people, however you want to split it. So there's more probabilistic, like a more simplicial, and there's the polynomials. Okay, so the probabilistic, I just have a distribution. In simplicial, I have a weighted simplicial complex, and in polynomials, I have G mu. Okay, so these are all really the same thing. Look at the marginals. So maybe I should say, instead of marginals again, we say, sorry, again. Conditioning on, say, I being S. This is really the same thing as taking a link in the corresponding simplicial complex and polynomials, as we just saw it. So it's like we take the derivative, differentiate. We have spectral independence. Let's say zero spectral independence. So in simplicial complex language, it's called like zero local spectral expansion. And here in polynomials, I have log concavity. And I guess if you can also generalize this, so say eta spectral dependence. This is eta over one local expansion. And I guess Nima has coined the term fractional log-concave. But really, just they're all the same thing, and we can sort of sometimes it's more convenient to like use one perspective versus the other perspective, but dictionary. Okay. Probably not. I mean, okay, I can say it very briefly. So it's if you look at the function, but now if I raise it to a power, each variable to a power, I want that to be log-concave. So if you chain rule and compute everything out, it's equivalent to okay. Okay, so I guess so maybe I'll first focus on log-concavity and zero local spectral expansion or zero spectral independence. So if I have the equivalence, then you might ask, okay, well then how do we prove log-concavity to begin with? And really, this just boils down to, this is where you can use some of this like high dimensional expander tools. You can use the trickle-down. Maybe I'll state it this way. Trickle-down. Maybe the polynomial version. So if I look at the Hessian of my polynomial, so I can view it as like a weighted graph. Okay. So this thing is connected as a graph. And now let me just say, let's look at the derivatives are all say log-concave. This is, I guess, in some sense, a special case where I'm restricting to lambda equals to 1, or sorry, lambda equals 0. Then mu itself is log-concave. So in particular, this will imply zero spectral independence and so on. Let me give you an example. So maybe let's maybe talk about like the example of spanning trees. We saw earlier how to do spanning trees for using, say, negative correlation, but if you use log-concavity, you can get sort of sharper results.
Question?
Yeah, go ahead.
What does that mean when a function is connected as a graph?
Sorry, yeah, so this is a matrix, right? Sorry, so maybe I should say I've evaluated this thing at all once. This is an n by n matrix. I can think of the entries as being the weights, the edge weights of a graph, and n vertices. And I'm just saying ignore the values of those weights as long as it's the, great, I'll have like an edge if it's non-zero or not, if it's non-zero, and then it's the graph.
For like any multilinear polynomial, or is the positivity
Positivity of coefficients is important. I guess I should say one thing about this is that you can actually generalize this beyond the multilinear setting. So as long as it's positive coefficients, but it's homogeneous, but it might have, say, x to the 5 or y to the 10 or something like that, this thing still holds true. So this kind of goes beyond the simplicial setting. This is so in some sense, this is one reason why you might want to formulate in terms of polynomials, because you can go beyond simplicity. Further questions? Well, I just want to briefly talk about spanning trees. So really, the main advantage of this theorem is now I can kind of reduce the complexity of my distribution. So if I just start differentiating and I get all the way down to even just a quadratic polynomial, then all I have to do is verify those quadratic polynomials are log-concave, and then deduce my whole thing, the whole polynomial is log-concave. Right. So really for spanning trees. And I'm not going to like spend too much time on it. I'm just going to briefly sketch the proof. So if you use just directly by trickle down, it slices verify concavity or basically G mu, where now I can differentiate out, say, so in this case, the polynomial is homogeneous of degree n-1. I just differentiate n-3 times to get a quadratic polynomial. And I just want to show that all of them are log-concave. Okay. So this thing is really the same thing. It's just I have this is G mu of, okay, so this is really, but this is the generating polynomial. For G, the uniform distribution of spanning trees of G after I've contracted E1 up to 3. I'm left with like a 2-vertex graph basically, and then verifying log-concavity is or 3-vertex graph, sorry. And verifying log-concavity is you can just like do it using like directly. Okay, so that's all I really want to say about this this technique. Any questions? So I'm gonna switch gears to talking about zero-freeness instead of log-concavity now. Okay. Are there any questions? Oh, say again? Oh, you read? Oh, right. Okay, sorry. Yeah. Okay, you're right. Okay. That's my fault. Sorry. Okay. I guess I want to say like one last thing regarding this. So I guess several people have asked me before, like, okay, so if everything is really just trickle down in the end, like, why would you ever, like, why do you need a polynomials formulation? And I guess like one nice thing is that the polynomials formulation sort of fits this kind of result into like a larger class of polynomials. Okay, so for instance, log-concavity manifests in many other interesting settings. So log-concavity elsewhere. And get volume polynomials. I mean, I won't define like what exactly they are, but these are very classically studied polynomials in convex geometry, determinantal polynomials. And I should also say that they have a lot of applications in algebraic combinatorics. So, for instance, so this is so really actually this theorem was actually was independently discovered by Junha, Peter Brandon. They called it Lorentzian polynomials. Since then, they've used it for a lot of applications in algebraic combinatorics, but I won't get into it. But I just want to say that so this polynomial framing of it, even though you can prove everything using trickle-down, it has sort of puts in like in perspective with respect to many other log-concavity phenomena that appear. Okay, so I want to switch gears to zero-freeness. So I have a polynomial that's very natural to ask about zeros. So I'm going to prove the following. Yeah, this is really first in the work of Ali Mohammadi, Anari, and Wong. And then we have some generalization extension to more general zero regions, but basically it goes like this. So suppose u of z is non-zero whenever. Now let me just focus on like the all ones point. Okay, so say zi are in just a small ball around 1. Okay, but it's constant. Okay, so delta here is like a small constant, but it's certainly much smaller than doing it for the entire half plane like we saw earlier. Okay. Then we introduce spectral independence. So I can say the infinity norm, that's okay. It's at most order of delta squared. Okay, so, and I'll show you an example of like how we can prove, like establish such a zero-free region later on. But for now, I just want to focus on
That's the operating norm.
infinity norm. Well, operating norm is also bounded. But yeah. So just to remind everyone. Norm. Okay. And so bound the max eigenvalue. Yes.
Check calling that the infinity norm, but to each their own.
I'll avoid writing that notation from now on for the rest of the time. Okay. I guess what's your definition of infinity norm?
Either the infinity norm as a vector or the
For matrix.
norm as an operator.
Operator.
But
That's the operator norm that you get if you put the infinity norm on the vector.
That's right.
like, so infinity to infinity.
Yeah. Okay. Yeah. If I can avoid writing another arrow in infinity. Okay. Okay. So I want to erase my dictionary. Okay. Okay. So basically the key idea is the following nice. So I'm looking at zero freeness in the complex plane, so I'm going to do some complex analysis. So really the key lemma. So this nice complex analytic statement, which sort of characterizes like or says something about the rigidity of complex functions, it says the following. So if I have a univariate function, say f, and I'm mapping the unit disk into the unit disk. Is this notation okay? So just this subset of complex plane, the complex numbers with norm at most 1. Is if f is holomorphic, let's say, smooth in the complex analytic sense, or differentiable or whatever, then for free, just from the fact that it's bounded and it's differentiable, then I can get a bound on the derivative of that. That's it. For free. Okay. So if I want to use this to prove something like spectral independence, I just really need to construct a suitable univariate function such that its derivative captures the influences. That's all I need to do. Right? So if I just want to use this thing as a black box. So suffices to, so I want to construct. So more formally, I want to construct maps. Let's call them phi and c. And I'll specify like the image, the domain, and range in a moment, such that, and maybe also, okay, so I'll say it this way. So such that if I look at f, which is equal to the composition of these maps, say what capital F in a sec. And we're okay. So let me just label these so they, so you know what they mean. So f, typically I want it to capture influences. Okay, so I want to think of, say, derivatives. Maybe I want to first, let's say, for fix and I. So because I'm upper bounding the infinity norm, I just need to show that for every arbitrary choice of I, the total influence is small. So I'm fixing I. I want this capital F to, when I differentiate it, to give me influences. Okay, so when I differentiate with respect to j, this should give me the influence of I onto j. What do I want out of phi? Well, I want to use the zero-freeness of my polynomial. So I just want to map the unit disk into my zero-free region. I guess just so that, right, so okay. So I can apply this lemma. And then I want this one to map the image of f back into the unit disk. So I want to map image f back into the unit disk. Okay. So if I can do this, then I can just do my chain rule and say that, okay, so this would imply that, if I again just imply the dilemma, 1 upper bounds the derivative of c at f, let's see, at all ones, times the summation over j of the influence I onto j times the derivative. So I guess phi here should be like a vector valued map, phi j derivative at 0. Okay, does this make sense? So all I'm saying is that if I want to apply this lemma, I just need to construct these suitable maps such that out of it I get a univariate function. And once I've applied it, what this says is all I need to lower bound the derivatives of these maps. Okay.
I'm confused about phi and c. Like, could you have just switched towards pick in a more general way and then just not have to deal with that, or like or choose?
So f typically is going to take inputs. So typically f is going to be, say, like log of my, so I say like, oh, so the choice of phi. Oh, okay, sorry. So your question is, could you have absorbed it? Yeah, okay, yeah, I see what you're saying. So yes, we can probably state a more general version of Schwartz pick, but then I still need to construct a suitable function here to satisfy the assumptions of that lemma, right? Like I can modify this with like maybe different choices of these regions, but at the end of the day, I still need to construct one that maps the appropriate region into the appropriate region. Yeah, sure. But it's so yeah. So I guess you're also kind of anticipating how I'm gonna construct these. I guess for simplicity, I'm just gonna take these together. They'll eventually be linear functions. They just sort of squash like the image sufficiently so that it gets stuffed into a ball. But okay, we'll see in a sec. I'm not sure if that.
I see. So phi is fixed, but psi you have to choose based on how you choose f.
Right. Yeah, definitely. So phi typically is like, it's just, there's nothing we can do about it because I need to map the unit disk into the zero-free region, because the zero-free region is it's the only place I have control over my polynomial.
I mean, this word pick, you can obviously translate it and also dilate it. So like,
Yeah, sure. Yeah.
So it's like psi is an f interact in a non-trivial way.
Yeah, sure. Yeah, that's right. I guess for our purposes, I'm just going to allow myself like a little bit of room. I'll put like delta over 2 here. Okay. So because, okay, I'll just say like what my choice for f is going to be. Okay. So I want differentiating f. Once I differentiate f, I'm going to get influences out of it, right? So I'm going to use the fact that, influences can be recovered by differentiating log of the generating polynomial. Okay. So recall that this kind of correlation is given by differentiating twice log of g mu. Once. Okay. So here will be my choice. So f of z just be I differentiate log of g mu only with respect to the ith coordinate, because once I differentiate with respect to j, I'll get my second derivative. And then for normalization purposes, divided by, say, the probability of I, just so I get an influence and not just a correlation or covariance. So, right. Try again. Oh, sorry. Yes. Let's see. Okay, so this is choice for f. Okay, so now you see I have log of generating polynomial, right? That thing is only well-defined if the generating polynomial is non-zero. It's only well-defined inside the zero-free region. So my choice for phi is like, I mean, there's not much you can do for it. Oh, okay, I mean, if you know more about your zero-free region, then sure you can do more, but a very natural choice, and just for simplicity, we'll just take this choice. I'm just going to take phi of j to be an affine function. So 1 plus over 2 times x. So the 1 is just to shift all 1s to 0. The delta is to squash it down. And then there's also going to be a choice of sign for Sj. So here, Sj, here you think of it as being, because I want to upper bound the absolute value of these influences. So I think of this as being the sign of this influence. Okay. And finally, what is my choice for C? So I just need to prove that maybe, okay, so I'll just say what my choice for C is and then prove that it'll actually work out in the way we want it to. Part for C is also just going to be a linear function. So it's just going to be some scaling by the probability of I times 2 times n. So let's just like, we're all friends, so this is constant. I'm just going to assume all these marginals are constants. Okay. So we're bound by constant. That's for convenience. Okay, so now I need to prove that everything makes sense, that this composition actually maps the unit disk into the unit disk, that it's holomorphic. So first, the fact that this function is holomorphic is clear now, because I'm mapping I'm mapping everything into the domain in which g mu is non-zero. So log of mu is g mu is also well-defined, analytic and everything. And so that's fine. I just need the only trickiness is establishing that it maps the unit disk into the unit disk. So, okay, so here's what I want to claim. So I can kind of just get rid of this. So it turns out these two things kind of cancel out. So I'm just going to prove the following claim, which is sufficient. So I look at this function and I look at its image on its zero-free region. This is contained in a ball that's not too large radius. Okay. Because once I can do that, then this is the correct scaling to squash it down back into the unit disk. Okay. It says that this function is not blowing up the image too much. Okay, so first, does everyone agree that if I can prove this, then we're essentially good? And this, clearly the derivatives of all of these maps are nicely bounded. Okay, so here's the proof. So suppose I have some y which is equal to this thing, and I can expand out what the derivative of log of g mu looks like, what it actually is. So respect to g mu, let's see, for some say zi in these balls so if I just rearrange, so this is the same thing. It's saying that, okay, so if I move everything across, g mu of z minus 1 over y, derivative of g mu of z equal to 0. Okay, so I have a polynomial and it's 0. Somehow I want to use the fact that g mu is non-zero inside this ball to give a proof by contradiction, basically. So suppose for contradiction, that say this y here has a large norm. Then I'm going to use this to construct a point in this zero-free region at which g mu is 0, which is a contradiction. Right? Okay. So there's a kind of a trick here that happens. So I'm going to sort of add and subtract following quantity. So this thing is equal to by g mu minus the partial I'm subtracting off all of the monomials that contain the variable xi. Now I'm putting it back, and notice how this part is really the same as this part. So this is xi minus 1 over y partial g. So what have I done? If you think of this as I've looked at all monomials and I only look at the ones that do not have xi. It's like I've removed xi from them. And then here I'm putting xi back, but I've shifted xi by minus 1 over y. Think of this as being exactly equal to g mu. For now, I have xi minus 1 over y, and then I've left all the other variables untouched. Sorry, I should not put x. I Can everyone see this? Is this too low? Okay, so I basically rewritten this polynomial as just an evaluation of my original polynomial at a slightly different point. The other key point is that I've assumed zi to be very close to be inside the zero-free region. And since y has a very large norm, 1 over y is a very small perturbation. So zi minus 1 over y is still inside my zero-free region. Okay. I'm claiming here is equal to 0. So that's contradicting zero-freeness for my polynomial. And so I'm done. Okay. All right, cool. Okay, so I just want to wrap it up or spend the last 15 minutes to give you an example of an application of this. And I guess we'll see an old friend, which is matchings again, just done a different way. And I guess I should also say that, if you know more about your zero-free region, not that it just contains a small ball, but it's actually so the original proof was looking at the case when the zero-free region is actually very large. It's a huge sector. And there you can, for instance, even avoid having to have this dependence on marginals. But okay. But basically the upshot is if you know more, then you can construct better maps here. Maybe let's do one example. Yeah. Okay, so yes, of course, same again. So just to remind you, let's say mu it's uniform over matchings, all matchings, not just perfect ones. Maximum degree delta graph. Through this example, I'll try to illustrate how you can establish these kinds of zero-free regions, because that's not an easy task. Okay, so the proposition that if I look at the matching polynomial, so this is three. Let's just say in a ball of radius 1 over the degree. So again, if my maximum degree is a constant, then I have a constant size ball around 1. And if I, so once again, use this to imply spectral independence, this is just another proof of doing matchings. Yeah, so there'll be a poor dependence. That's right. Yeah. So basically, how would you prove such a thing? And this is, as far as I'm aware, essentially all proofs have the following flavor for these multivariate zero-free regions. Typically try to start from something which is sort of obviously zero-free, like a product of linear forms, and then slowly deform that polynomial and then track how the zeros evolve. Okay. The recipe. Start. Let's say a product linear forms, linear functions. Basically, something obviously free. then form. Okay. So let me just say first, what is the starting polynomial that I'm going to inherit zero freeness from? Okay. For matchings, I can always think of a matching as follows. So maybe I have a graph that looks like this. I don't know. I want to look at matchings on this graph. So I can think of it as follows. I'm going to build matchings. I'm going to split each edge. So I divided each edge into a half edge. And I'm just looking at matchings on this new graph, satisfying the additional constraint that two edges that came from the same edge, they have the same status.
Have the same what, sorry?
The same status. Okay, so I have this matching here. I'm looking at I wanted to look at matchings here. I can think of it as looking at matchings here, but now I need so let's say it's like a vertex U, V, V. So this is an edge E. So I divided this edge E into, say, I've identified which vertex it came from. Then this edge is now edge comma V. These two like half edges, so to speak. And a matching here is just a matching here with the additional constraint that these two half edges, they're either both in the matching or they're both not in the matching. Okay. So with this view for matchings, and the point is that sort of now if I just look at matchings on a star, it's a very easy object to look at. Right? So the polynomial I'm going to inherit zero freeness from is the following. So I look at the product or vertices in the graph. I look at 1 plus summation over edges incident to that vertex of a variable. Okay, so this is like kind of like a product of linear forms. I can analyze its zero-free regions very easily. And now the deformation is just going to, I'm going to slowly collapse these variables. So I'm going to start merging variables xue, xve back to a single variable xe. Okay, I'm going to track the zero-free region, the evolution of the zero-free region. Okay, so how am I going to do that? This is a very classical method for establishing zero-free regions in statistical physics. It's called the Osano-Ruel contractions. Nice tool. This was first used to prove something called the Li-Yang theorem, or give an alternative proof of the Yang theorem, which is a major result in statistical physics. So it's called Osano-Ruel contractions. Says the following. So I'm merging only two variables at a time. So I can actually just study a very simple bivariate polynomial. So the claim goes as follows. So if, let's say, the polynomial a plus bz1 plus cz2 plus bz1 z2 is non-zero whenever, have to check which exactly way it goes. Whenever, say, z1 is not in some set k1, and then z2 is not in some set k2. Then I'll give some examples of these zero-free regions in a moment. So basically, if I have sets for which this polynomial is non-zero, then I merge z1 and z2 into a single variable, then the polynomial a plus b of z is non-zero if z is minus of k1 times k2. So this object is just xy, so x1, y not going to prove this lemma, but basically the point is that this allows me to merge variables and I still get to track how the zero-free region evolves. So let me just give you a couple of examples. So if, say, K1, K2, they're both equal to the complement of the unit disk, then K1 times K2 minus Z. So for instance, if it so happened that this polynomial, this simple two-variable polynomial is zero-free inside the entire unit disk, then by doing one step of contraction, it's still zero-free in that unit disk. That's one example. Another example is that if, say, K1, K2 are big half plane over here, this is equal to 0, maybe I have some gap epsilon, then this implies K1 minus K1, K2. This is equal to, you compute it out, it turns out to have like a parabolic region around the zero-free, around the real axis. Okay, so if it's zero-free in a little bit more than a half plane, then it's going to be zero-free in a parabolic region. But the point is that, okay, so these are just some examples of like how you track these sets. Okay, so I guess at this point, all I need to tell you, I mean, if you take this as a given and you sort of inductively do this contraction step, then all I need to show you is like, what is the zero-free region for this? And I'll just say here, here's the lemma. So I just need to say zero-free region for each of these linear forms, right? Because it's a product. So for all vertices V, 1 plus summation over E x VE is non-zero if E exactly a region of this form. So in everything a little bit more to the, sorry, it's this. Basically a zero-free region of this form where the epsilon here depends on the degree. So epsilon is equal to 1 over the maximum. I guess here is something like. Okay. Does anyone see the proof of this? Exactly, right? So like if all the real part of all the inputs are larger than 1 over delta, there's no way you can beat the 1. Exactly. Okay. So I think I'm out of time. That's essentially all I want to say. Maybe Alex. Yeah.
Questions? Okay, if there are no questions, let's thank Kuikui again. We'll meet again tomorrow for the last day of the bootcamp.